Welcome to today's MINDS seminar. It's my great pleasure to introduce Fanny Yang, currently an assistant professor in the CS department at ETH. Before joining ETH, she was a postdoc in Stanford and also at ETH. And before that, she got her PhD at Berkeley with Martin Wainwright. So she will tell us about rethinking the effects of inductive bias. And so we're very much looking forward to your talk. The floor is yours.
Thanks a lot, Felix, for the kind introduction, and to all the organizers for inviting me to this great seminar that has kind of helped us to survive through the pandemic of no talks in person. So the story I want to tell you about today is based on two papers that is led by my student Konstantin Donhauser and written together with other current and former students in our group, Guillaume Wang, Stefan Stojanovic, and Nicolo Ruggeri. So before we jump into our story, I want to recap some classical wisdom. Right? So assume you want to recover a ground truth function. In this case, this would be the red dashed line. Given only samples that are noisy, which are the black crosses, right? So assume you have a very flexible function class to fit these data points, especially if you can fit them perfectly. What you don't want to do is to fit all the points perfectly, right? So this is classical wisdom. The reason is that in this case, we have a polynomial of very high degree, that this blue function, the final model, would be very far off from the true function, that is the red line. So in order to get closer to the red curve or to generalize well, what you need to do is to regularize and avoid fitting this noise. Right, so here you're adding a rich penalty, and what you get is a function that is much closer to the red line, but is not fitting the black crosses perfectly. And this allows for better generalization, or in some cases even optimal. So now this is the classical story, avoid fitting noise. So let's look at very flexible functions in modern machine learning and what people actually observe there. And so what are very complex models in modern machine learning? One example, very prominent example, is of course neural networks. So let's look at classification using neural networks, where we train a neural network on image data, where we artificially add label noise. So for example, CFAR10, you can actually achieve 99% test accuracy. So it's unclear if it intrinsically has noise or not. So in order to talk about noisy interpolation, we really need to add artificial noise and to see what happens in that case. And so what we do is we train a first order method to minimize the cross entropy loss, for example, on this image data set. And then we look at how changing the size of the network affects the error on the test set. So here what we see on the x-axis is the size of the network in terms of the width. So, so we start with the ResNet 18 standard width is roughly at around, say, 5. But then we make it wider and wider and see what the effect is of this enlargement on the test error. And so what I want you to look at here is only at the blue line, the blue curve, which is the model at convergence of running this first order optimization method. Just focus on the blue line for now. And let's look at what happens. So at a particular point, which is an additional information you do not see on this plot, at ResNet width parameter 10, you actually reach the interpolation threshold, which means that you're able to fit all the noisy training data perfectly. So this is just additional information. And once we know that this is the interpolation threshold, we can make two observations. So the first one is that this, do you see my cursor? Yeah, hopefully. The first one is that the blue curve is actually going down, right? So the error on the test set is decreasing as we increase the flexibility of the model and the width of the model. Okay, so this is perhaps surprising to start with because you already have perfect flexibility to train noisy data at 10, but at width 10, but if you increase it even more, then you get better test performance. So this is what we call sometimes double descent. In this for neural networks here, what we want to focus on is the second descent, and we don't care about the first descent. Okay, so this is one observation. The second observation is if we now not only look at the blue curve, but also the dotted or the dashed red line. The dashed red line is the error of the model where we choose for each width parameter the best stopping time. So it's essentially, you can think of the best regularization for each network size. You pick that model and you look at the test error there. So it's early stopped. And you can see, of course, it's better. The best stopping time is better than a particular stopping time. But the degree of how much it is better, this gap between the blue and the red line decreases as we increase the width. Okay, so here what we say, so here we want to focus on this part of the plot. For very large models, interpolation is not worse than regularization, and we call this phenomenon harmless interpolation throughout the talk. So I have these two observations, and the question now is, are these observations unique to neural networks? And so in this slide, I just want to quickly show that this is not specific to neural networks, but in fact, you can even observe such phenomena for linear models. In particular, the simplest that you can think of, that any data scientist or machine learning, a beginner is going to learn about, which is linear regression. So here we're switching gears a bit. We're going to the regression setting, but we're doing the same thing. So we run gradient descent on the square laws now and initialize at 0. And the data that we're fitting now is generated by essentially a linear model where the covariates are drawn from standard Gaussians, and we have Gaussian noise, just a very standard model. And then we want to look at the error as a function of dimensionality of the features. Okay, so D is the number of features or the dimensionality of the covariates, and N is the number of samples. So here we again have a regime where we are under-parameterized. So D is smaller than N. In this case, if N is very, very large, which is D over N is close to 0, we have very small MSE, which is what we would expect classically. And as N goes closer to D, you also see that the MSE is blowing up, essentially because the variance is blowing up. What happens afterwards is interesting and less studied, at least before the work on over-parameterized models started. And first of all, we want to note D equal to N, so D over N equals to 1 is the interpolation threshold. And what we see here is actually that the two observations also hold. So the black line is the model at convergence, and here the green dashed line is the early stopped one, or you can think of the optimally regularized one. So here we also see a second descent, or actually just a descent after the interpolation threshold. And we also see harmless interpolation for large D over N. Right, so the key of this slide is that these two observations that we just saw in neural networks, you can also observe for linear models. And so this is interesting. So we started with neural networks. They're on the end of being on the extreme of being very hard to analyze, so it's very high complexity because you're using a first order method on a non-convex loss. It depends a lot on hyperparameters, on initialization, etc., to analyze such neural networks. In particular, we have feature learning, which makes everything much harder than if you have fixed features. In that case, over-parameterization we define as essentially the width of the hidden layer. So if we increase the width, we increase over-parameterization. On the other spectrum, or on the other end of the spectrum of the analyzability, we have linear interpolators. So these don't have some of the problems of neural networks, which is optimization works well in the sense that we have a convex optimization problem that finds the global minimum. And so we can just look at the unique minimizer of that convex optimization problem and analyze generalization performance of those. Instead of learning features for linear interpolators, we have fixed features, but the number of features essentially can serve as a proxy for over-parameterization. If you think of a D as the actual features and not the raw input, but actually D as the number of features after going through a feature map, then D essentially is giving you kind of the flexibility of the model fitting these covariates. And in this case, how much larger D is compared to N is the degree of overparameterization. So strikingly, up until recently, we did not have any explanation for this behavior of linear interpolators either, even for the simple setting. Hence, we do not understand why these observations occur. And so in this talk, I'm hence just going to focus on the right-hand side, on the easiest models to analyze, and try to tell you about some of the insights that we found when we try to analyze those. And hopefully these insights or intuitions can transfer to a particular hypotheses about explanatory hypotheses for neural networks that then can be verified experimentally later. This is the goal of the talk. We're now going to focus entirely on linear interpolators. Okay, so what's the high-level outline for the rest of the hour? So I'll start with providing previous intuition for overparameterization, which is a particular Bias-variance trade-off as a function of the degree of overparameterization. This was already previously known. And then I will add a complementary intuition to the picture, which is based on our work. That is essentially saying that we have a bias-variance trade-off that is induced by varying the inductive bias. And I will define what we mean by inductive bias in the next few slides. And after that, I will support this intuition, or this rather high-level story, by some concrete bounds that show how fast or how well we can actually trade off this bias and variance using the inductive bias and finding an inductive bias that is moderate. Right. So I should say that if you have any questions at any time, feel free to stop me. So I don't have that many slides, so it's more important that everybody is following. Okay, so let's start with the first intuition, which is based on previous work for minimum L2 norm interpolators. So maybe just one word, why minimum L2 norm interpolators were first studied. Well, for one, if you start to do gradient descent with initialization at 0, then the final solution you get, if D is larger than N, is the minimum L2 norm solution. So that is one natural reason to study it. Another reason is actually that you can find a closed form, and it's rather convenient to analyze it that way. And so people started studying minimum L2 norm interpolators and found the first very interesting intuition. So what they compared are these interpolators, which is gradient descent until convergence, with ridge regularized estimators, which is essentially when you early stop. There you can find, at each stopping time, you can find corresponding lambda, the penalty coefficient. So here we have the same picture. Now I cut off the first part, the underparameterized part that I don't want to discuss. And this was the picture that we saw. So the interpolating solution, the MSE of that solution has a descent after interpolation. And when D over N grows, we have that the regularized estimator is similarly performing as the interpolating estimator. Okay, what is actually the new model? I also already mentioned, we have the noisy observations of a linear ground truth, W star, a scalar product with the covariates and with Gaussian noise. So here the Gaussians are isotropic. And so what people have basically proven with their bounds or shown is that what's happening is that the bias is, well, the variance is actually decreasing as we increase D over N. Right? So the bias is relatively simple. You would expect the bias to increase because as you increase dimensionality, it's harder and harder to find the signal because you have more and more freedom to search for a particular signal, so it's harder to find it. But the variance part is really the main contribution of a lot of those works. And so what's the intuition for why the variance decreases? I don't have a slide for this. I just want to explain it in words. So perhaps let's start just thinking about a fixed n. The number of samples is fixed, right? And so the variance is kind of close to the norm of the estimator that purely fits noise. Right, so yeah, let's just look at x w equal to noise. Let's assume w star is 0 for now. So if you look at the interpolator for d equal to n, for example, there's only one interpolator, one interpolating solution that has a particular L2 norm, right? But if you now increase the dimensionality, what you're doing is you're adding degrees of freedom to fit this noise, right? So you could always take the interpolator at d equal to n and set all the new dimensions to 0. This is also a feasible solution, but adding dimensionality helps you to find solutions that could have a much smaller norm than the one that is forced to only use d of those, right? So if you have 2d, you can use the new d dimensions to fit noise with a smaller L2 norm. So essentially the additional degrees of freedom allow you to have smaller norm of this noise fitting W, which then translates to a smaller variance. And this is really the reason why the variance decreases as d increases for fixed n. And so if you look at, so basically the variance decrease can explain both of the observations that we saw. So first, the second descent, or the descent right after interpolation here, is due to the variance decrease because the variance is dominating the bias in that regime. And also the harmless interpolation part can be explained as well. So if you look at large d over n, the variance is close to 0. And what that means is the regularization term here, the lambda, that is essentially trying to avoid fitting noise, is not really that meaningful anymore because the effect of noise is not that large anyway. Okay, so the decrease in variance is really the key to understanding minimum L2 norm interpolators and why these two observations happen. Okay, so this is the variance story. So are we happy now, right? So we have proven, or at least others have proven that variance decreases, and this already gives us an intuition for why these two observations happen. But as opposed to neural networks, what we actually find is that we are not happy in this case because the generalization performance of the interpolating estimator is very poor compared to what you could achieve. The Bayes error is really close to 0 in this case for our synthetic setting. So the problem is that the bias gets really large in this regime where d over n is large, right? And so the bias increases, and in our case to something that is unacceptably high. And so we need to dig a bit deeper. So we want to understand in a regime where interpolators can generalize well, whether we can show the same two observations, because neural networks really do well in the large model regime or large width regime. Okay, so what's missing here? So of course, if you have a high dimensional problem and you're trying to just use a minimum L2 norm estimator or interpolator or a ridge regression, you're not adding that much prior information about the ground truth. And without any prior information about the structure of the ground truth, you have too many directions to search in and you don't know where to focus on. So estimator has essentially no clue. This minimum L2 norm or this L2 norm minimization is not encouraging any particular structure. That's the problem. So what people have looked at in order to get a better generalization for L2 is that they could show some consistency bounds, which means that the error actually goes to 0 for very specialized or spike covariances. So these are the works that are in the bottom row. But the problem with these works is that in practice, you don't know whether the covariances are exactly of this form. In practice, sigma is just given to you, the covariance of the features, and you have to deal with it. And you have to basically try to find or hope for an interpolator that works for this particular sigma. So we want to essentially swap or change the perspectives. Instead of varying sigma, we want to vary interpolators. So previously, people have looked at the fixed minimum L2 norm interpolator and varying covariance to get good generalization, and we will turn it around. Before we do this, let's just continue on this structural point and take a step back and ask the question, what kind of interpolators can actually learn the ground truth well if we are in very high dimensional settings? And of course, I'm mentioning structure, and a lot of the people in the audience are familiar with that. A classical intuition of high dimensional statistics is that you can only estimate well if you assume something about the ground truth, that the ground truth has a simple structure such as sparsity, and your estimator is matching that particular structural simplicity, that your estimator is encouraging that particular structural simplicity, and we call this matching inductive bias. Okay, so this is just our definition of inductive bias. Others may have other definitions, but this is what we'll use throughout the talk. Okay, so you have to match, you have to have the estimator or interpolator that matches this inductive bias or this structure. So let's just keep sparsity as our running example for structural simplicity throughout the talk now. So what we started with is minimum L2 norm solutions. In this case, the L2 norm doesn't utilize at all this prior knowledge about sparsity. Even if the ground truth is sparse, it cannot exploit that knowledge. As opposed to that, the L1 norm encourages sparsity structure, as we all know from classical theory, or not classical, but of the last 2 decades. There's been a lot of work on this. So that's why we talk about the L2 norm as having weak or essentially no inductive bias, and the L1 norm having very strong inductive bias for our particular ground truth that is sparse. Okay, so just to recap, what can we achieve in the setting when we are looking at minimum L1 norm interpolators and lasso? So in the noiseless case, what people have shown is that minimum L1 norm interpolation, also called basis pursuit, can achieve perfect recovery with high probability if we have the number of samples to be roughly proportional to the sparsity times LD. So this is well known, and what happens when your data is now noisy, then you should not do interpolation, but do regularization with the lasso. So you add a penalty term, lambda times the L1 norm, and you achieve an estimation error rate that is minimax optimal, which is of the order S log D over N, if you have chosen the right lambda here, the penalty coefficient. So what's the intuition behind this? And what are you exploiting here? So what we're exploiting here is the lambda, that you have flexibility to change your lambda according to your noise or your sample size. And let's recap this very old intuition of the bias-variance trade-off here, which is the same as the one that I stated in the beginning. On the x-axis, you really have varying model complexity. Or here, you're just allowing the L1 norm to be larger or smaller. So as we go in the right direction, we are increasing lambda, and we want to see what happens to the bias variance and the MSE and the error. So as we increase lambda, right, we are putting more weight onto having a simple structure than fitting the data. So we are decreasing the fitting of the noise. At the same time, when we increase lambda, we increase the bias as well, right? Because the true W star is not at some point not going to be in that set anymore, this feasible set. On the other hand, if you increase lambda, you are attenuating noise, and hence the variance goes down. And so the perfect lambda is essentially somewhere in between that minimizes the MSE. So this is the story for regularized estimators, but interpolators don't have the flexibility to vary lambda because they're forced to fit perfectly y equal to xw, right? So they cannot attenuate noise by choosing some optimal lambda. Instead, the interpolators are equivalent to setting to basically taking lambda, the limit, to 0. So in that case, we are forced to have something like this instead. So if you just took the L1 and let lambda go to 0, the lasso, and let lambda go to 0, you would get basis pursuit. But what we want to add here is the component of varying the norm, right? So as we said before, there's the p equal to 1, so the L1 norm and the L2 norm. The L1 norm has very good inductive bias towards the ground truth solution. The L2 norm has the benefit of attenuating noise very well. And so basically that's why we want to choose P as sort of reflecting the strength of the inductive bias towards sparse solutions. So P equal to 1 is corresponding to a very strong inductive bias. And as we go to the right towards P equal to 2, we are decreasing the strength towards sparse solutions. There. And so what's happening here with the bias, the same story, P equal to 2 doesn't give you any information about the ground truth. So as you go towards P equal to 2, the bias would intuitively get larger. And the opposite is true for the variance. And so here, the intuition is somewhat similar to what I mentioned before for the L equal to 2 case, P equal to 2 case, where we increase the effective dimensionality. So if you think for fixed D and N, you're starting at P equal to 2, say D is much larger than N, and we know that P equal to 2 gets a very low variance. And now we walk towards P equal to 1. So P equal to 1 is essentially forcing your solution to be sparse. So what that means is it's letting you look at fewer directions or allowing fewer directions in order to fit the noise. So in that sense, because you are giving less flexibility to fit noise, it's forcing your norm to be larger to be able to fit the noise. Okay, so this is again a bit high level, but this is the intuition why for a very strong structural or inductive bias, the variance goes up to have less flexibility to fit noise. Okay, so here we have essentially just discussed a new kind of bias variance trade-off that occurs for interpolators if you allow the inductive bias to vary. And so the MSE we would expect to also follow a U-curve. And in this case, just to summarize, the increasing P or decreasing structural bias plays the role of increasing lambda of attenuating noise. And so now the rest of the talk, we just want to see how well can we actually do for P equal to 1, P equal to 2 we already know, but I will recap that in a second. And then see, okay, how good is the sweet spot here? So how well can we generalize compared to, for example, the minimax optimal rate of the lasso with interpolators with P between 1 and 2. So this is the agenda for the rest of the talk. Okay, so if there are any questions, please feel free to ask anytime.
Will you say something about computational comparison? Because I think that L1 has a linear program and sort of least squares is also fairly easy, and P in between, is it comparable in complexity or?
It's still a convex program, so you can essentially just throw Mosaic at it and at solving that program. But yeah, it's probably not optimized at this point comparatively, but it's not it's not the focus of the talk here. I just want to focus on the statistical properties for now. But it's a good question, yeah. And so what's interesting also in the classification setting is that some have shown, for example, Progressor, I think, that it's also an implicit bias of a particular optimization algorithm on the cross entropy loss or classification losses, that you get that as a result. Yeah, I haven't looked into detail here, but it's a good question. There was another question. Okay, so then let's look at the bounds for P equal to 1, or actually start with P equal to 2 and then complete the picture. So before we go there, let's just clarify what our setting is. So I'm simplifying the setting by a lot. We're only looking at regression, for example. Our papers also have classification, and we also only look at one sparse ground truth, where of course we don't know the location. But we also have results for S-sparse solutions, where S is constant. So this is a simplified setting just to have a slightly cleaner presentation of the results. Okay, so the function space, again, we consider our linear models. And the data is generated by the linear model with Gaussian covariates, isotropic Gaussians, and Gaussian noise. So the Gaussianity is pretty important, and that's something we cannot extend. But that's primarily the main thing that we cannot extend. We think that we can also extend that to spike covariances, but we're still working on it for prediction error. Okay, the degree of overparameterization here, we use beta, which is the exponent. So d is of the order n to the beta. So the exponent beta reflects the degree of overparameterization. If beta is equal to 1, we have the interpolation threshold, and as beta grows beyond 1, the dimensionality is much larger than n. And what we consider are minimum LP norm interpolators for p between 1 and 2. So we have a strictly convex problem, so we have a unique solution. And then the performance measure will be the prediction error. In the case of isotropic Gaussians, the prediction error is equal to the estimation error. That's also interesting because then you can also look at robustness, etc. I'm not going to talk about this, but yeah. So this is our setting, and all of the results will be presented for the setting. Okay, let's start with previous work on p equal to 2, just to recap, so that we're on the same page. You've seen this plot before. Now for p equal to 2, for isotropic Gaussians, the estimation error, or in that case equal to the prediction error, is always bounded below by a constant that's bigger than 0 for any overparameterization degree beta. And this holds even as the number of samples goes to infinity. So in the asymptotic limit, or high dimensional asymptotic limit, we also have an error that's bigger than a constant. Okay, so this is definitely worse than lasso, which is goes to 0 with 1 over n roughly, and that's just to keep the context. Okay, and people, of course, as I mentioned, you can get away with changing this covariance, but we don't want to do that. We want to stick with one kind of covariance and see what we can do. Okay, so this is for p equal to 2. You basically have a constant rate. And what happens for p equal to 1, before our work in the IID noise case, there was essentially a gap between lower bounds, which are of the order 1 over log d over n. So if you plug in d equal to n to the beta, you essentially have 1 over log n order, versus upper bounds that were of constant order. Now I have to mention the upper bounds were established for a particular setting that is different than ours, which is adversarial and vanishing noise. But there are no other upper bounds around that were matching the lower bounds, and even there were conjectures in those papers that even for the IID noise case, the upper bounds should probably be, or the lower bounds should actually be constant. So it wasn't clear were the lower bounds not tight or were the upper bounds not tight. And so we resolved this problem and showed that actually the lower bounds were tight. And in particular, this is simplified theorem, is that there exists universal constants that whenever n is larger than some constant, we have this estimation error bound or prediction error bound, which is of the order, or actually equal to sigma squared over log d over n plus some order term that is decaying faster. So what's important to note here is that we have lower and upper bound that matching in the leading constant for Gaussian and X, for Gaussian covariates. And interestingly, if we look at experiments, the bounds are also tight beyond Gaussians, but our technique crucially relies on Gaussian, so it's quite hard to show anything beyond that, but we're working on that, or actually trying to see if we can extend that, but it turns out to be really hard. I just want to note that the same bound holds for classification, where we look at the directional, so basically we look at the normalized W hats and W stars. So you also have a rate of 1 over log d over n. So now if we go back to our original question with the two observations, do we now show them? Right. Were we able to show that? So if we plug in d equal to n to the beta, so here I plugged it in, you get 1 over beta, essentially beta minus 1 times log n as the rate. So as beta increases, the error decreases, or the rate gets a little faster. Okay, so in some sense, we have a second descent after, we have a descent after interpolation. And that's also the reason for that is similar as the intuition that I discussed for p equal to 2, that as d effective grows, the variance decreases. Now, it doesn't decrease as fast as for p equal to 2, but it still decreases. The other point that we saw in neural networks is that for large models, interpolation becomes harmless and close to regularization. Now, so is this true in this case? Well, it's completely wrong. In particular, we have to compare this rate with the lasso rate. Oh, yeah. When we plug in d equal to n to the beta, we essentially have 1 over log n for the interpolator versus 1 over n for the, so s is 1 here. So we have 1 over n for the lasso. So we have a huge gap. And so here, this is what we've seen so far. For p equal to 2, we have a constant rate. For p equal to 1, we have a very slow rate, but it is a bit better than p equal to 2, in particular because the bias is better. But the question is, of course, can we do something, can we have interpolators between 1 and 2 that could have a rate that is more comparable to the regularized case, to the lasso? And if I ask that question, I guess you already expect that the answer is yes, to some extent. And so this is what I'll discuss next. This paper is just published at ICML. And so here we look at minimum LP norm interpolators with p between 1 and 2. Also, same setting, d of the order n to the beta, and beta bigger than 1. Now the beta cannot be that large, depending on the p, but it's still a good range. And if n is large enough, we can again plug in n to the beta and look at error rates that are now of the order 1 over n to the alpha. So we have polynomial convergence compared to log convergence. So much faster, but now we don't want to know how large this alpha is. And so instead of writing formulas, because the formulas are relatively hard to parse, I plotted the rates in a figure here that I will go through really slowly. I just want to mention that these rates are both upper and lower bounds, so they are tight for the lower bound for the particular estimator. So these are tight bounds. Okay, so what do we see in this plot? So I want you to first ignore the nice colorful lines and only focus on the line at 0 and 1. So the y-axis is the rate exponent. So if alpha is 0, we have essentially a constant rate up to log factors, and that is what we just showed for p equal to 1 and 2. So this is the constant rate for p equal 1 or 2. And the rate 1 over n, which is alpha equal to 1, is the minimax rate that we can achieve with the lasso. Right? So as we go down, the rate becomes better. And so basically, previously, we had this huge gap between this constant or up to log factors constant rate compared to the regularized rate. So now with p between 1 and 2, we're filling this space. On the x-axis, we have the overparameterization degree beta. And so what we plot here is for different p's, we fix p's, we vary the beta, and we look at how the rated exponent looks like. So I'll say in a minute why we plotted it this way and not the other dual way, where we have p on the x-axis and beta as the lines. So now let's just walk slowly through this plot. And let's say we fix some beta. So here it's close to 3. And what we can learn from this plot is, or what we can read off, is that I can, of course, I have the rates for p equal to 1 or 2, and I have the minimax rate, but in between, if I increase p from 1 to 1.01, for example, I'm actually really close to 1 over n rate, so alpha equal to 1. And as I increase towards 2, I again get closer to the constant rate. So here's p equal to 1.1, and here it's p equal to 1.2. Right, so this is for fixed beta. I can read off that p equal to 1 and 2 are worst. If I increase a little bit, the p from 1 to 1.01, then I get a very fast rate immediately. So there's a kind of a sharp transition here. The other thing I can read off is that for beta close to 2, the rates are really close to 1 over n, or rather close to 2 and beyond. And in particular for classification, we can actually show that they're exactly 1 over n. Okay, so classification is slightly easier because you only care about the direction. And so you can actually get exact rates 1 over n up to log factors. Okay, so that's already said. The technique applies to classification. We already have the results, and we're working on extensions to spike covariances and S-bars, W stars. Okay, so these were our rates. And what do we learn from that? So again, going back to our 2 observations, do we now see those reflected in the rates? So the first one was that we have this descent after interpolation. So interpolation is when beta is equal to 1 here, right? And indeed, as you increase over parameterization, right, towards 2, the rate exponent gets larger, alpha gets larger, and the rates get faster, or the convergence, statistical convergence gets faster. And that is if you pick the best interpolator between 1 and 2 in each case. Or in this case, actually, for p equal to very close to 1.01, you get this second descent after interpolation. So we take the first observation. Now, the harder one was the second observation, as I already said. And this one, actually, we finally also take in that the interpolator for p very close to 1 gets a rate that is close to the minimax optimal rate of a regularized estimator as the so. Okay, so we were able to show the 2 observations in a regime where the actual generalization error or generalization performance is good. Okay, so these are the good sides of the theorem or theorems. And there's some caveats though. So I have here n large enough. In this case, the n not large enough is not as nice as the previous one, where we just needed n larger than some constant. In fact, what we require is that 1 over log d is smaller than p minus 1. So what that means is we require a very large d. So either very large beta or very large n. And in particular, if you want p equal to 1.01, then this d, you can compute how large that is. That's pretty enormous. And so this is one of the caveats. And this comes in from having to concentrate or show concentration bounds of the LQ norm of a Gaussian vector in a very tight way, and to get high probability bounds. So this is also a reason, this caveat is a reason why we cannot plot the figure the opposite way around and have p on the x-axis with a fixed beta and find the minimum, because we can only plot p up to the point of 1 over log d plus 1, and instead of going all the way to 1. And so we cannot actually find the minimum or the best p for a given beta. But this is just a technical caveat that I wanted to mention, so we're not at the end of the journey yet. Okay, so just to recap theoretical bounds that we have now accumulated through the last 15 minutes. So we started with the constant rate at p equal to 1, and then a 1 over log n rate for p equal to, constant rate for p equal to 2, and 1 over log n rate for p equal to 1. And then we completed the picture with having polynomial rates of order 1 over n to the alpha in between. And so now let's look at the bias variance trade-off that we see here with experiments. So I already mentioned that in some way for p equal to 1, the noise sensitivity is much larger because you have fewer degrees of freedom than compared to p equal to 2, where you can search in all directions. The rotational variant, you can search in all directions. And so in the case of p equal to 1, even when you have d very, very large, the sensitivity to noise is still large. This is still large and larger than p equal to 2. And so this is what we showed in this experiment, where we have d very large, 20,000, and only 400 samples. When you compare the sensitivity to increasing in noise, you see that the L2 norm is essentially constant in terms of the MSE, but the L1 norm really suffers a lot by just a little increase of the noise. Well, not little, but increase of the noise. So it's much more sensitive. And this is also what leads to the bias-variance trade-off now plotted experimentally. So here we also have synthetic experiments for d equal to 5,000 and n equal to 100. And there, just ignore the blue line for now. We have exactly the cartoon picture that I showed you before, now experimentally confirmed. The orange line, the solid line, is the MSE, the noisy MSE, so the MSE when you're fitting noisy labels, noisy observations. And then you have the bias that goes up with the decreasing inductive bias strength. And you have the variance that goes down when p goes to 2. That's exactly what we showed in the cartoon pictures, now just with some actual numbers and using experiments. The noiseless MSE is here just to say that it follows the usual intuition that p equal to 1 is best. But p equal to 1 is best for interpolators only holds if you have noiseless data. So once you add a bit of noise, the best inductive bias shifts towards 2. That's kind of why we have the blue line here as well. Okay, so this is the optimal point shifts towards 2. And we've shown now experimentally that there is a bias-variance trade-off as a function of the inductive bias. So this is for regression. And I mentioned that we also have results for classification. In particular, we ran some real-world experiments for max margin interpolators, which are essentially the also minimum of some norms subject to the SVM constraints. And here the generative model is essentially to have random label flips in. We start with a Gaussian or isotropic Gaussian as your covariant distribution. You define some theta star or W star, which is your decision boundary, your true decision boundary that is sparse. And then you just add random label flips, or you can also add logistic noise to it, normal logistic model. And what you get is for synthetic experiments, for this kind of experiment, you get a similar picture. So you saw before, the blue line is in the noiseless case when we don't have any label flips. And when we add 10%, so sigma equals 0.1 is equal to adding 10% label noise, you see that the best inductive bias shift towards 2. Okay, this is synthetic experiments, but we also have real-world experiments on a leukemia data set, which is also highly high-dimensional. And what we did is essentially also just using the vanilla data set, you get very good performance, or a very kind of good performance, where the best P is at 1. But if we add artificial noise, 5% noise, random label flips, then again, you see the best P shifts towards 2. So this kind of phenomenon seems to also hold in finite DN settings, even though our results are for D very, very large, as I said in the beginning. And it also holds for real world data sets to some extent. Okay, so this is basically most of what I wanted to say, just to summarize what we learned today. So I first started to motivate linear interpolators, in particular minimum norm interpolators, by saying that we see the same observations or similar observations as in neural networks for these linear interpolators. So hence, and we don't have much intuition for those or any explanation. So we want to study these models first. I want to stress, perhaps I did not mention it yet, I want to stress that we are not advocating, instead of using lasso, to use interpolators and cross-validate P. Right, so it's perfectly fine to use lasso and cross-validate lambda. The only reason we're studying, or the effect of P on interpolators, is that in the case where we have to interpolate, we want to know which interpolators could do well. So our motivation was not to kind of come up with a new way to find sparse solutions. That's definitely not that. So we just want to get some understanding and intuition for when interpolation works well. So that's what I wanted to add. And so for this, so we discussed first how over-parameterization can decrease variance and leading to a kind of new bias-variance trade-off as we vary the degree of over-parameterization. However, previous work that does this does not take into account what happens when we try to change the interpolator and try to use different interpolators. In particular, previous work does not get or achieve good results or good generalization results when we have isotropic Gaussians and a fixed with a fixed covariance. So our work is essentially adding a new bias-variance trade-off intuition to the picture of interpolators, and basically says that in addition to this bias-variance via over-parameterization, we have bias-variance via the strength of the inductive bias. And so in our case, in the linear case, the inductive bias for sparse ground truth is clearly p equal to 1 versus p equal to 2. Of course, as you go to neural networks and images, it's much less clear what the right inductive bias is, or what a strong inductive bias even is. And this is what we leave to future work to study whether this intuition could also be an explanatory hypothesis for neural networks or not. And so with this, I want to end the talk, and here are the papers that I discussed today. And so very welcome to ask any questions you might have.